Hello. Today I'll show you what is the Laplace transform of a natural log of x times I. Now, Laplace transform is the following. Laplace transform of a function f is the integral from 0 to infinity of e to the negative sx times f of x dx. So, now we've got to find the Laplace transform of natural log of x times I. Well, first of all, we have to see what a natural log of x times I is. So, natural log of x times I is just natural log of x times I. So, we can break this into two separate natural logs. Natural log of x plus natural log of I. Now, this is simple, but what is this? Well, let's see. Natural log of I can be rewritten as e to the I times the angle I has in the complex plane, which is pi over 2. So this is same as e to the I pi over 2. The natural log and they cancel, so natural log of I is just I times pi over 2. So, let's do the Laplace transform of this. This is the integral from 0 to infinity of e to the negative sx times ln of I dx plus the Laplace transform of e to the negative sx of natural log of x dx. So, let's first find this, because it's pretty easy. So let's name this first integral and this the second integral that we need to find. So let's start with first. Okay. So this is the integral from 0 to infinity e to the negative sx times I times pi over 2, the natural log of I dx. Now, this, we can pull at the 1 over 2 outside, so it's 1 over 2 times the integral we have here, I times pi dx. And let's first see, this is just a constant, so let's first see what this is. The integral of e to the negative sx dx. Let u equal negative sx du negative s dx. So that will give us 1 over s times e to the u dx, not dx because we're in the u world, so du and this will equal to just e to the u over s. Then we plug in negative sx for u, and we find that it's negative sx over s. Now, we found what this is, so the answer to this is just this times I times pi, and then we put in the limit. So it's the limit as a approaches infinity of e to the negative sa times pi times I, although this is not very important, but just put it anyway, times 2s. This isn't important either, but okay. You can see as a approaches infinity, this term becomes 0. So 0 times pi I is 0, and 0 divided by 2s is still 0. So this is 0. Then what we need to do is do for the lower bound. We just did for the higher bound of the integral. So the answer will be 0 minus e to the negative s times 0 times pi I over 2s. Now, e to the 0 is just 1. So what we get is negative pi I over 2s. And this is our answer to our integral here, to our first integral. This is it. So now we have to find the second integral. It's a bit harder. So, integral from 0 to infinity of e to the negative sx times natural log of x dx. Well, let's start by substituting. Let u equal sx, du will then equal s dx. And if we solve for dx, dx will be equal to 1 over s du. So, let's plug in this into this integral. So this becomes integral from 0 to infinity of e to the negative u times natural log of u divided by s, because u is sx, so we have to cancel the s to get just ln of x, times 1 over s du. So we can bring out the 1 over s. 1 over s times the integral of 0 to infinity of e to the negative u. And inside the natural log, when two things dividing, it's just the natural log of one thing minus natural log of the other thing. So it's just natural log of u minus natural log of s du. So now we can break this integral into two separate integrals. So the first one will be just 0 to infinity of e to the negative u of ln of u du minus ln of s times the integral of 0 to infinity because ln of s is a constant, so it can be brought out, of e to the negative u du. So this is just 1 over s times integral from 0 to infinity of e to the negative u ln u minus ln of s, because this it just the integral of e to the negative u. So distribute this, 1 over s integral of 0 to infinity of e to the negative u natural log u du minus natural log of s over s. Now, this is fine, but what exactly is this? This is a very hard problem, which it's very, very hard to do. So, another way of writing this is that this integral is just negative gamma. So we just assign a name to this integral called negative gamma. This gamma is the Euler-Mascheroni constant, which is approximately 0.577. And yeah, so I'm not going to calculate this. I'm just going to tell you it's equal to negative gamma, because it will take too long if I calculate it. So let me explain what exactly is gamma. So gamma is the difference of the harmonic series with the natural log as n approaches infinity, because the harmonic series is divergent and it increases very, very slowly, just like natural log of x. So people have thought that we can compare those two functions. So the constant is just the difference of those two functions which are very close to each other. The difference just about 0.577. So that's why the Euler-Mascheroni constant exists. Now, it's a bit more complicated, so why this constant shows up here? So I'm not going to explain now. So, if we now know the value of this, and we know the value of this, so together we know this, which is the answer to the second integral, and we know the answer to the first one, we finally get that the Laplace transform of natural log of x times I is equal to negative pi I over 2s, our first integral here, plus the second integral, which as we found, is negative gamma plus natural log of S over S. So this is your final answer. Please subscribe for more videos like this.